What if I told you the universe hides objects so destructive they could erase entire galaxies in the blink of an eye? Out there, beyond the serene glow of stars and the gentle swirl of nebulae, lurk forces of unimaginable power, cosmic monsters that defy our understanding of reality. Picture a single object so dense it warps space itself, or a storm of radiation so fierce it could sterilize planets light years away. These aren't the plots of science fiction. They're real, lurking in the darkness, waiting to be uncovered. Today, we're embarking on a journey to the edge of the unknown, where the laws of physics twist into nightmares. From the chilling silence of black holes to the violent fury of hypernovae, the universe is far from the peaceful expanse it appears to be. Every corner of the cosmos holds dangers that make even the most terrifying earthly disasters seem trivial. Imagine a single burst of energy so powerful it outshines an entire galaxy for a moment, or a wandering rogue planet, icy and alone, capable of hurling entire solar systems into chaos. These aren't just threats, they're cosmic titans reshaping the fabric of existence itself. But why should we care about these distant terrors? Because understanding them is understanding our own fragile place in the universe. These forces sculpt galaxies, forge elements, and in some cases, hold the power to end life as we know it. Over the next 25 revelations, we'll uncover the deadliest objects lurking in the void, each more astonishing than the last. Some are familiar, like the monstrous black holes at the hearts of galaxies. Others are so strange they challenge everything we think we know, so brace yourself. What you're about to witness will change how you see the cosmos forever. The universe isn't just beautiful, it's breathtakingly dangerous, and this is your front row seat to its darkest secrets. At the heart of our Milky Way galaxy, an invisible predator lies in wait, Sagittarius A, a supermassive black hole with an appetite so vast it could swallow our sun 4 million times over. This cosmic giant doesn't just bend the rules of physics, it shatters them, warping space and time into a lethal funhouse where gravity becomes an inescapable executioner. Picture a star, bright and proud, drifting too close to its event horizon, the point of no return. In an instant, the black hole's tidal forces stretch it like taffy, a process scientists grimly call spaghettification. The star's outer layers are ripped away, swirling into a glowing disk of superheated plasma before vanishing into the abyss. But Sagittarius A isn't just a destroyer, it's a conductor of cosmic chaos. Its gravitational pull orchestrates the motion of hundreds of billions of stars, holding our galaxy together even as it consumes whatever dares to cross its path. Astronomers have watched helplessly as entire gas clouds spiral toward it, their atoms torn apart in a frenzied death spiral. And yet, despite its ferocity, this black hole is eerily quiet much of the time, lurking in shadows like a predator conserving energy for its next meal. What makes it even more unsettling, we're hurtling toward it right now. Our solar system orbits the galactic center, inching closer with each passing millennium. But don't panic, we're still 27,000 light-years away, a safe distance for now. Sagittarius A reminds us that the universe isn't just vast, it's filled with forces that humble even the mightiest stars. And if there's one lesson this silent monster teaches us, it's that in the cosmos, darkness doesn't just hide secrets, it hungers. Imagine a cosmic lighthouse so powerful its beam could strip atoms apart from halfway across the galaxy, not with light but with pure magnetic force. Meet the magnetar, a neutron star turned nightmare, where the laws of physics buckle under pressures so extreme they make black holes seem almost tame. These stellar corpses pack the mass of our sun into a city-sized sphere, spinning faster than a blender blade and armed with magnetic fields a quadrillion times stronger than Earth. One wrong move within 1,000 miles of this monster, and your very molecules would unravel like thread in a shredder. The birth of a magnetar is a cataclysm unto itself. When a massive star collapses in a supernova, its core doesn't just form a neutron star. It becomes a twisted, hypercharged dynamo. The star's magnetic field, compressed into this tiny, spinning wreckage, amplifies to mind-bending levels. But the true terror lies in what happens next: starquakes. The magnetar's crust, under unimaginable strain, occasionally cracks like a frozen lake, releasing gamma-ray bursts that outshine the entire Milky Way for a fraction of a second. In December 2004, a magnetar 50,000 light-years away unleashed such a blast. Despite the distance, it still rattled Earth's upper atmosphere with more energy than our Sun emits in 250,000 years. Satellites flared with false alarms, as if the cosmos had flicked a switch to remind us of its power. What makes these bursts so lethal? It's not just the radiation, it's the way they warp space itself. The magnetar's magnetic field twists the quantum vacuum around it, creating a zone where matter behaves in ways we've barely begun to understand. If one of these cosmic time bombs lurked within 20 light-years of Earth, its periodic eruptions would cook our planet's surface sterile. Yet for all their violence, magnetars are also cosmic alchemists. Some scientists believe these magnetic monsters might be forging elements heavier than iron in their turbulent guts, elements that eventually seed new stars and planets. So while they're among the universe's most terrifying objects, they're also silent architects of the very stuff that makes life possible. A brutal reminder that in the cosmos, creation and destruction are often two sides of the same coin. Somewhere in the void between stars, an invisible hunter drifts Gaia BH1, the closest known rogue black hole, silently carving a path through our galactic neighborhood. Unlike the supermassive beasts anchored at galaxy centers, this wanderer has no fixed address, no cosmic leash. It moves like a phantom, betraying its presence only by the way its gravity tugs at the occasional passing star. With a mass 10 times that of our Sun crammed into a sphere smaller than a city, it warps the fabric of space around it, bending light and bending fate for anything that strays too close. Imagine a black hole not as a distant celestial fixture, but as a free agent barreling through space at hundreds of thousands of miles per hour with no predictable trajectory. Its movement is governed by ancient violence, the kick of a supernova that blasted it loose from its birthplace, sending it careening into the cosmic wilderness. Gaia BH1 currently sits a mere 1,500 light-years away, close enough to raise eyebrows but far enough to spare us for now. Yet its existence forces a chilling question: how many more of these dark nomads lurk undetected, their paths intersecting with unsuspecting star systems? The danger isn't just the black hole itself, but the chaos it leaves in its wake. As it passes through a system, its gravity would act like a wrecking ball on planetary orbits, flinging worlds into deadly new paths or hurling them into the void. Even a near miss could destabilize a star's delicate dance with its planets, triggering a cascade of collisions or ejections, and if a star drifts too close, the black hole's tidal forces would siphon off its outer layers, creating a swirling accretion disk of superheated gas, a temporary beacon in the darkness before the star is consumed entirely. What makes rogue black holes uniquely terrifying is their stealth. Without the glowing debris of an accretion disk, they're nearly impossible to spot until their gravity distorts the light of background stars, a subtle effect even our best telescopes struggle to catch. Astronomers estimate there could be hundreds of millions lurking in our galaxy alone, each a potential agent of cosmic upheaval. They remind us that the universe isn't just a gallery of wonders, but a wilderness where unseen predators roam, rewriting destinies with the quiet, inexorable pull of their darkness. When a dying star explodes, we call it a supernova, a brilliant death that briefly outshines entire galaxies. But what if I told you there's something even more terrifying? Meet the hypernova, a cosmic detonation so powerful it makes ordinary supernova look like firecrackers. Picture this: a single hypernova unleashes 100 times more energy than its smaller cousin, channeling it into beams of destruction so intense they can be seen clear across the universe. These aren't just explosions, they're gamma-ray blowtorches, cutting through space with enough force to rewrite the chemistry of planets light years away. At the heart of this apocalypse is a star so massive it collapses not into a neutron star, but straight into a black hole. The infalling matter doesn't just implode, it rebounds in a jet of plasma moving at nearly the speed of light, piercing through the star's outer layers like a bullet. These jets, glowing with the fury of 1 trillion suns, are the source of those deadly gamma-ray bursts. And here's the chilling part: they can last for minutes, even hours, far longer than the milliseconds typical of most cosmic explosions. That sustained energy is what makes hypernova not just spectacular but lethal on a galactic scale. Take WR-104, a star system 7,800 light-years from Earth. It's a ticking time bomb, a pair of stars where one is already on the verge of collapse. If that star goes hypernova, and if one of its gamma-ray jets happens to be aimed at us, the consequences would be catastrophic. Even from that distance, the radiation could shred Earth's ozone layer in seconds, exposing all life to the sun's unfiltered ultraviolet rays. Ecosystems would collapse, food chains would unravel, and the damage would linger for decades. But here's what really sends a shiver down the spine. Hypernova don't need to hit us dead-on to be dangerous. A burst within 6,000 light-years, just a stone's throw in cosmic terms, would still bathe our planet in enough radiation to trigger mass extinctions. The Earth has likely endured such events before. Geological evidence hints at past ozone depletion linked to gamma-ray bombardments. And while WR-104's jets aren't currently pointed our way, stars like it remind us that the universe doesn't need malice to be deadly. Sometimes all it takes is being in the wrong place at the wrong time, when a dying giant decides to flip the cosmic kill switch. Among the most violent events in the cosmos, gamma-ray bursts stand in a league of their own, blinding flashes of energy so intense they can outshine 1 million galaxies combined for a few fleeting seconds. These aren't scattered explosions but focused beams of annihilation, firing like cosmic rifles across billions of light-years. When a hypernova collapses into a black hole, or when neutron stars spiral into each other in a catastrophic merger, the resulting jets of plasma and radiation narrow into twin lances, each no wider than a few degrees. If one of those beams crosses paths with a planet, the results are apocalyptic. Evidence suggests Earth may have already suffered such an encounter. Around 440 million years ago, during the Ordovician period, life on our planet was flourishing until suddenly it wasn't. Marine fossils from that era reveal a staggering die-off, with 60% of all species vanishing almost overnight. For decades, scientists puzzled over the cause. Then they noticed something peculiar. The extinction pattern didn't match asteroid impacts or volcanic winters. Instead, it mirrored the effects of extreme radiation damage, a thinning ozone layer, mutated plankton skeletons, and a sudden collapse of shallow water ecosystems. The smoking gun, a gamma-ray burst, likely from a hypernova or merger within 6,000 light-years, could have bathed Earth in deadly rays for less than a minute but left scars lasting millennia. The Fermi Gamma-Ray Space Telescope has captured these events in gruesome detail. Its data reveals waveforms spiking with energy equivalent to the Sun's entire lifetime output compressed into seconds. One particularly chilling burst, JABI 080319b, unleashed enough power in 30 seconds to outshine every star in the observable universe combined. A flare so bright it briefly blinded Fermi's sensors from 7.5 billion light-years away. Had that burst occurred within our galactic neighborhood, its ultraviolet afterglow alone could have ignited global wildfires while its gamma rays ionized the upper atmosphere, triggering acid rain and climate collapse. Yet gamma-ray bursts aren't just destroyers, they're also cosmic messengers. Their light carries encoded details about the early universe, helping astronomers map the structure of spacetime itself. And ironically, the same elements forged in these explosions, gold, platinum, uranium, eventually seeded planets like ours. So while they wield the power to sterilize worlds, they also carry the ingredients for new ones. A reminder that the universe's most dangerous forces are often the very ones that make life possible. If you survive their wrath, imagine a cosmic furnace so bright it outshines 1,000 Milky Ways, a single point of light blazing with the fury of 100 trillion suns. This is a quasar, the visible signature of a supermassive black hole feasting on an entire galaxy's worth of matter. At the center of this maelstrom, gas, dust, and even stars spiral into oblivion, heating to millions of degrees before vanishing beyond the event horizon. But here's the twist: not all that material is swallowed. Some gets hurled back into space at nearly light speed, forming jets of plasma that stretch across intergalactic distances like celestial flamethrowers. Take 3C273, the first quasar ever identified and one of the most powerful. Its jet, a searing beam of particles and radiation, extends 200,000 light-years, twice the diameter of our entire galaxy. If you could see it with the naked eye, this jet would appear longer than the full moon in our sky, despite being 2.5 billion light-years away. But its beauty is lethal. The radiation pouring from that jet includes X-rays and gamma rays potent enough to strip atmospheres from planets tens of thousands of light-years away. Any world caught in its path would be scoured clean, its oceans boiled into space and its crust bathed in enough ionizing radiation to fracture DNA in seconds. What makes quasars truly terrifying isn't just their power, it's their unpredictability. Unlike the steady glow of stars, these active galactic nuclei flare and dim as their black holes gorge on fresh material. A sudden influx of gas could trigger a burst of energy capable of sterilizing entire galactic arms. And while most quasars are ancient relics from the early universe, their modern counterparts, active galaxies with weaker but still deadly cores, prove the threat isn't confined to the distant past. Our own Milky Way's central black hole, Sagittarius A, was likely a quasar in its youth, and though it's dormant now, future collisions with other galaxies could reawaken its hunger. Yet quasars are more than destroyers. Their light, traveling billions of years to reach us, acts as a time capsule, revealing secrets about the universe's infancy. The very elements that make up our bodies were forged in the hearts of galaxies energized by these monsters. So while they wield the power to erase life, they also illuminate the cosmic processes that make life possible, a paradox as breathtaking as it is humbling. In the grand tapestry of the universe, quasars remind us that brilliance and brutality are often inseparable. Deep in the cosmic shadows lurks an invisible killer, dark matter, the mysterious substance that outweighs all visible stars and galaxies 5-1. While we often think of it as a passive scaffold holding the universe together, there's a terrifying possibility. What if certain clumps of dark matter could suddenly unleash bursts of lethal radiation? Picture a dense knot of these invisible particles drifting unseen through our galaxy. According to some theories, if these clumps collide or decay in just the right way, they could release gamma rays with enough energy to sterilize entire star systems in an instant. One of the most unsettling ideas is the concept of dark stars, not the shadowy remnants of dead suns, but hypothetical objects fueled by dark matter annihilation itself. Imagine a star that doesn't shine through nuclear fusion but glows faintly from the heat of dark matter particles annihilating at its core. These bizarre structures, if they exist, could grow to monstrous sizes, hundreds of times wider than our solar system. And here's where it gets ominous. When their dark matter fuel runs out, they wouldn't just fade away. They might collapse catastrophically, triggering a supernova-like explosion powered not by fusion, but by the sudden release of pent-up dark energy. Astrophysicists have even theorized that certain patterns of gamma-ray bursts, those ultra-powerful cosmic flashes we've detected, could be the death cries of these dark stars. In 2007, researchers analyzing data from the Fermi telescope noticed something odd. A handful of gamma-ray bursts with energy signatures that didn't quite match known supernova or neutron star collisions. Could these be the fingerprints of dark matter annihilation events? The unsettling truth is we don't know, yet the real danger lies in the unpredictability. Unlike black holes or hypernovae, we can't see these dark matter clumps coming. They don't emit light, and their gravitational pull alone might not betray their presence until it's too late. Simulations show that if a dense dark matter blob passed through Earth, even briefly, the resulting particle collisions could generate enough radiation to mutate DNA on a global scale. Some scientists speculate that past mass extinction events might bear the scars of such an encounter, a silent, invisible visitor rewriting life's history in a single pass. Yet for all their destructive potential, these dark matter anomalies could also be keys to unlocking the universe's deepest secrets. Their hypothetical explosions might explain mysterious cosmic signals we've struggled to decipher for decades. And if we ever detect definitive proof of dark matter annihilation, it would revolutionize our understanding of everything from galaxy formation to the very fabric of reality. So while the threat is real, so is the promise, because in the cosmos, the greatest dangers often hide the brightest revelations. Floating above and below the Milky Way's core like two colossal hourglasses, the Fermi bubbles stretch 25,000 light-years each, a pair of cosmic ghosts glowing with gamma rays. But their eerie light isn't just radiation. It's the death cry of antimatter, the universe's most volatile substance, annihilating on contact with ordinary matter. These bubbles are thought to be remnants of an ancient eruption from our galaxy's supermassive black hole, a cataclysmic event that might have sprayed antimatter particles into space like shrapnel from a celestial grenade. And trapped within those towering structures could be clouds of positrons, antimatter counterparts to electrons, each one a potential bomb waiting to collide with a single stray atom. The moment matter and antimatter meet, they vanish in a flash of pure energy governed by Einstein's most famous equation, E equals mc squared. To grasp the scale of this destruction, consider this: 1 gram of antimatter annihilating with 1 gram of matter releases energy equivalent to the Hiroshima nuclear bomb. 43,000 tons of TNT unleashed in a microsecond. Now imagine not grams, but vast clouds of antiparticles adrift in space, their combined destructive power dwarfing anything humanity has ever conceived. A single antimatter meteorite the size of a pebble striking Earth would detonate with the force of a hydrogen bomb, leaving a crater miles wide and bathing the landscape in lethal gamma radiation. Yet the real terror lies in the Fermi bubble's composition. Astronomers using NASA's Fermi telescope have detected excess positrons streaming from these structures, particles that shouldn't exist in such concentrations unless antimatter is actively forming or accumulating there. One theory suggests the bubbles are fueled by dark matter particles colliding and decaying, spawning antimatter as a byproduct. Another proposes that Sagittarius A star's past eruptions accelerated particles to near light speeds, creating antimatter in their wake. Either way, these bubbles serve as a stark reminder that antimatter isn't just a laboratory curiosity, it's a lurking cosmic hazard. What stops these antimatter reservoirs from detonating like a universe-scale minefield? Distance and vacuum. Space is so empty that positrons might travel for millennia before encountering a regular electron to annihilate with. But introduce a dense medium, say, a molecular cloud or a wandering star, and the results could be spectacularly violent. In 2018, astronomers observed a strange gamma-ray flare near the bubble's edge, possibly triggered by antimatter meeting a pocket of interstellar gas. The resulting energy surge briefly outshone 1,000 suns, a flicker of what could happen if larger antimatter caches found richer fuel. Here's the chilling paradox: antimatter isn't just a destroyer. It's also a key ingredient in medical PT scans and might one day power spacecraft. Yet the same properties that make it useful also make it perilous. The Fermi bubbles remind us that the universe doesn't just harbor dangers we can see, it conceals others woven into the fabric of space itself, silent until the wrong particles brush too close. And that's a threat no shield can block, because annihilation doesn't leave debris to deflect. It leaves only light, a flash marking where existence briefly tore itself apart. Spinning at thousands of revolutions per second, a pulsar isn't just a dead star. It's a cosmic Gatling gun firing beams of radiation with pinpoint precision across the void. Born from the supernova death of massive stars, these neutron star remnants pack more mass than our Sun into a sphere no wider than Manhattan, their unimaginable density warping space-time into a funhouse mirror. But their true lethality lies in their rotation. As they spin, their powerful magnetic fields channel particles into twin beams that sweep across space like lighthouse beams from hell. Except these aren't guiding ships to safety. Their sterilization rays capable of cooking planets light years away. Few pulsars embody this danger more vividly than Quasar B 1957+20, nicknamed the Black Widow. Located about 6,500 light-years away in the constellation Sagittarius, this millisecond pulsar completes nearly 600 rotations every second, so fast its surface moves at roughly a quarter the speed of light. Each rotation whips its particle beams through space, but here's where it gets gruesome. Those beams aren't just radiating into empty darkness. They're methodically disintegrating the pulsar's binary companion, a brown dwarf star being slowly vaporized by the relentless assault. Chandra X-ray observatory images reveal the horror show in stark detail. A swirling maelstrom of superheated plasma being torn from the dwarf star, forming a glowing tail of stellar debris stretching hundreds of thousands of miles into space. The Black Widow's killing mechanism is twofold. First, its radiation pressure bombards the companion star's surface, boiling away its outer layers at a rate of about 1 Earth mass every million years. Second, the pulsar's powerful wind, a supersonic flow of charged particles, acts like a cosmic sandblaster, further eroding the star and carrying the stolen material away into interstellar space. What remains is a ghastly spectacle. The brown dwarf's corpse glowing in X-rays as it's reduced to a planetary mass cinder, its fate sealed by the pulsar's unrelenting fury. But the Black Widow isn't unique. Astronomers have catalogued dozens of similar redback and Black Widow pulsars, each at different stages of stellar cannibalism. Some, like Quasar J1311-3430, have already consumed their companions entirely, leaving behind eerie, pulsar-powered graveyards. Others, like Quasar J0224+62, show telltale X-ray signatures of freshly ablated material still orbiting their murderous hosts. Together, they paint a terrifying picture. In the Milky Way alone, thousands of these celestial predators may be lurking, their beams sweeping silently through the darkness, each rotation bringing some hapless stellar companion one step closer to oblivion. What makes these death beams especially chilling is their reach. While the immediate devastation occurs within binary systems, pulsar winds can extend light years into interstellar space, carrying enough energy to disrupt molecular clouds and potentially sterilize any fledgling planetary systems in their path. The Crab pulsar, born from a supernova observed on Earth in 1054, still pumps out enough high-energy radiation to ionize gas clouds thousands of light-years away. And in 2008, astronomers detected a pulsar whose gamma-ray beams momentarily outshone the full moon despite being 15,000 light-years distant. Yet pulsars aren't just destroyers. Their precise rotations make them cosmic timekeepers, helping astronomers test Einstein's theory of relativity. The materials they liberate from their victims enrich the interstellar medium with heavy elements. And their extreme environments serve as natural laboratories for physics we can't replicate on Earth. This duality defines so much of the universe's deadliest phenomena. The same forces that obliterate also create, the same objects that kill also illuminate. The Black Widow may be a murderer, but its deadly dance reveals secrets about the universe's most violent transformations, reminding us that in space, even destruction can blaze a trail of understanding. When two neutron stars spiral toward each other in a death dance, the universe doesn't just witness a collision, it experiences a cosmic alchemy furnace unlike anything else in existence. This is a kilonova, an explosion so violent it forges the heaviest elements in the periodic table in mere seconds. Picture two city-sized objects, each more massive than our Sun, crashing together at a third the speed of light. The impact doesn't just shatter them, it triggers a runaway nuclear reaction that sprays gold, platinum, and uranium into space like sparks from a forge. In fact, the gold in your jewelry likely originated from such an event billions of years ago. But these mergers aren't just celestial jewelry shops, they're also gamma-ray factories. As the neutron stars merge, their immense magnetic fields get wound up like cosmic rubber bands, snapping to launch jets of plasma at nearly light speed. These relativistic jets, narrower than a pencil but stretching millions of miles, become particle accelerators of unimaginable power. When astronomers detected GW 170817, the first neutron star merger caught by gravitational wave observatories in 2017, they witnessed this duality firsthand. The collision, located 130 million light-years away, produced gravitational ripples in space-time, while its afterglow revealed signatures of freshly minted heavy elements. Follow-up studies estimated this single event created over 10 Earth masses of pure gold and 100 Earth masses of platinum, glittering evidence of the universe's most extreme chemistry experiment. Yet for all their creative power, kilonovae wield apocalyptic potential. If one occurred within a few thousand light-years of Earth, the radiation blast would unfold in two lethal phases. First, the gamma-ray jets, lasting less than 2 seconds but packing enough energy to rival a supernova, would strip away our planet's ozone layer. Then, the expanding debris shell would arrive days or weeks later, bathing the atmosphere in X-rays and ultraviolet light for months. The combined effects would trigger global acid rain, collapse food chains, and potentially lead to a mass extinction. Even more unsettling, we'd have zero warning. Gravitational wave detectors like LIGO can only spot these mergers after the fact, meaning the first sign of danger might be the gamma rays themselves hitting our upper atmosphere. What makes kilonovae uniquely terrifying is their efficiency. Unlike supernova, which release energy in all directions, these events focus their deadliest output into narrow beams. A planet directly in the path of those jets would suffer millions of times more radiation than one positioned even slightly off-axis. And while the odds of Earth lining up with such a beam are astronomically low, the universe has a way of reminding us that low probability doesn't mean zero. The fossil record shows periods of abrupt biodiversity loss that still puzzle scientists, some of which align suspiciously with traces of interstellar radiation spikes. Yet kilonovae also represent one of nature's most astonishing balancing acts. The same process that could sterilize worlds also seeds the cosmos with the building blocks of life. Elements like iodine and uranium, crucial for biology and planetary geology, are thought to originate primarily in these collisions. Even the jet mechanisms that make kilonovae so dangerous may play a role in distributing these materials across galaxies. So while we fear their destructive potential, we also owe our existence to them, a paradox as beautiful as it is humbling. In the end, kilonovae embody the universe's relentless cycle, death on a cosmic scale, giving birth to the very ingredients that make new life possible. Lurking in the interstellar void, untethered to any star, rogue planets drift like cosmic outcasts, dark, frozen worlds with the power to rewrite the fate of entire solar systems. These planetary nomads, ejected from their birthplaces by gravitational chaos, roam the galaxy alone, some carrying temperatures colder than liquid nitrogen while others simmer with volcanic fury. But one hypothetical rogue planet has haunted astronomers for decades: Nemesis, the Sun's purported dark companion. The Nemesis hypothesis suggests our star might have a distant twin, a failed brown dwarf or massive planet orbiting far beyond the Oort cloud. Every 26 million years or so, as the theory goes, Nemesis's gravity would perturb comets in the outer solar system, sending a deadly rain of icy bodies hurtling toward the inner planets. The chilling part: this cycle suspiciously aligns with Earth's mass extinction events, including the asteroid impact that wiped out the dinosaurs. While Nemesis remains unproven, we've confirmed the existence of other rogue planets like CFBD SIR-2149-0403, a gas giant 7 times the mass of Jupiter wandering just 100 light-years away. Without a host star to warm it, its surface hovers at around 400 degrees Celsius, far colder than any planet in our system. Yet rogue planets aren't always frozen. Some, propelled by tidal forces from their violent ejections, might maintain molten cores for billions of years, fueling volcanic eruptions that dwarf Earth's most active supervolcanoes. Picture a world where the sky is perpetually black, the only light coming from rivers of lava cutting across a landscape with no sunrise or sunset, just endless night. The true danger of these drifters isn't just their loneliness, it's their potential to invade other star systems. A rogue planet passing through our solar system wouldn't just be a spectacle, it would be a gravitational wrecking ball. Even a distant flyby could destabilize the Oort cloud, triggering a comet storm that could bombard Earth for millennia. And if one ventured closer, its gravity could tug planets like Jupiter or Saturn off course, disrupting the delicate balance that keeps our system stable. Simulations show a rogue planet just twice Earth's mass passing within 1 billion miles could alter Earth's orbit enough to trigger an ice age, or worse, send us spiraling toward the Sun. Yet for all their destructive potential, rogue planets might also harbor secrets about life's resilience. Some could maintain subsurface oceans, heated by radioactive decay or tidal flexing, creating isolated pockets where extremophiles thrive. Others might serve as future way stations for interstellar travel, frozen orbs where civilizations could mine resources in the darkness between stars. The universe, it seems, always balances its monsters with possibilities. And as we scan the void for these wandering giants, we're reminded that the cosmos doesn't just contain threats, it holds mysteries waiting to rewrite everything we think we know. In the silent darkness of a binary star system, a ticking time bomb runs down, a white dwarf, the smoldering corpse of a once bright star, slowly stealing matter from its companion. This cosmic thief isn't just growing heavier, it's approaching a catastrophic tipping point. At 1.4 times the mass of our Sun, the pressure in its core becomes so extreme that dormant carbon atoms suddenly ignite in a runaway nuclear chain reaction. In less than a second, this carbon detonation rips the white dwarf apart with the force of 10 billion suns, a type I supernova so bright it can outshine entire galaxies. We've witnessed the aftermath of such explosions before. The remnant of Tycho's supernova, named after astronomer Tycho Brahe, who documented its sudden appearance in 1572, still glows in X-rays 450 years later. Chandra Observatory images reveal an expanding shockwave 15 light-years across, hurling stellar debris at millions of miles per hour. But what makes this particular supernova chilling isn't its past violence, it's the realization that the same process could unfold dangerously close to Earth. The death toll of a nearby Type I supernova comes in 3 waves. First, the initial flash of ultraviolet and X-rays would hit our atmosphere like a cosmic tsunami, ionizing the upper layers and triggering nitrogen oxide production that annihilates the ozone layer within weeks. Next, months later, the expanding shockwave would bombard Earth with high-energy protons, further irradiating the surface. Finally, the supernova's debris shell would arrive years or decades later, lacing our solar system with radioactive iron-60, an isotope found in deep-sea sediments that suggests our planet has weathered such explosions before. Astronomers have identified several potential supernova progenitors within the lethal 30 light-year radius. One particularly unsettling candidate is Ik Pegasi, a binary system 150 light-years away where a white dwarf orbits perilously close to a main sequence star. While currently outside the danger zone, its trajectory brings it closer over millennia, a slow-motion threat future civilizations may need to confront. Even more ominous are the silent threats we haven't yet detected. Astronomers estimate hundreds of white dwarfs likely exist within 30 light-years, many hidden behind interstellar dust clouds that obscure our view. Yet Type Ia supernova aren't just destroyers, they're cosmic mileposts. Their consistent peak brightness allows astronomers to measure vast intergalactic distances, revealing the universe's accelerating expansion. The very explosion that could end life on nearby planets also helps us map the cosmos. This duality defines so many of the universe's deadliest phenomena. The same processes that create also annihilate, the same light that guides also burns. And in the silent dance of binary stars, we're reminded that destruction often begins with something as simple as a starving star stealing one atom too many. Among all the universe's lurking terrors, none is more chillingly absolute than the vacuum decay bubble, a hypothetical catastrophe that wouldn't just destroy matter, but rewrite the fundamental laws of reality itself. Picture this: somewhere in the cosmos, a random quantum fluctuation nudges the Higgs field, the invisible energy field that gives particles their mass into a lower energy state. The moment this happens, a sphere of new physics begins expanding at light speed, its boundary an inescapable wall where every atom, every force, even the fabric of spacetime itself is instantly reconfigured. This isn't science fiction. Current particle physics suggests our universe's vacuum might not be in its most stable configuration. Like a pencil balanced on its tip, the Higgs field could theoretically tip over into a lower energy state if given enough of a push, perhaps by extreme conditions in a particle collider or a cosmic event releasing sufficient energy. The resulting phase transition would spread outward uncontrollably, not as fire or explosion, but as a redefinition of existence. Inside the bubble, quarks might no longer bind into protons, electromagnetism could cease functioning, and the very concept of matter as we know it would dissolve into something unrecognizable. The math behind this nightmare comes from combining quantum field theory with general relativity. Calculations suggest the Higgs field's current state is metastable, technically stable for now, but not in the lowest possible energy configuration. At energies above 100 billion gigaelectronvolts, levels last seen in the universe's first trillionth of a second, the field could become unstable. And while everyday physics keeps us safe, certain high-energy astrophysical events or experiments might, in theory, create the critical spark. What makes vacuum decay uniquely horrifying isn't just its scale, but its inevitability once triggered. Unlike gamma-ray bursts or rogue black holes, there's no distance that guarantees safety. The decay front advances at light speed, meaning we'd have zero warning before it reached us. One moment we'd exist, the next moment, the concept of we would no longer have meaning. Astronomers scanning the cosmos have even looked for evidence of such bubbles in distant galaxies, searching for unnatural voids where physics might operate differently. So far, the universe appears uniformly stable, but the possibility lingers like a shadow across fundamental physics. Yet paradoxically, this existential threat also represents a frontier of human understanding. Studying vacuum metastability pushes our knowledge of quantum fields to their limits, potentially revealing deeper layers of cosmic architecture. Some theories even suggest multiple vacuum states could explain why our universe's constants are so finely tuned for life. We might exist in one favorable bubble among countless others where physics forbids complexity. The vacuum decay scenario forces us to confront an unsettling truth: the universe's fragility. All it might take is one quantum hiccup in the wrong place, and reality as we know it could unravel like a sweater with a loose thread. But until that moment, if it ever comes, this spectral danger serves as a reminder. The same laws that make existence possible also hold the seeds of its absolute erasure. Not with a bang, not with fire, but with a silent reordering of the cosmic rules themselves. Racing through the void at 150 kilometers per second, Smith's cloud isn't just another wisp of gas, it's an intergalactic bullet aimed straight at our galactic doorstep. This colossal hydrogen structure, spanning 11,000 light-years from end to end, carries enough raw material to birth 2 million stars like our Sun. Discovered in 1963 by astronomy student Gail Smith, this invisible behemoth was initially mistaken for a faint radio signal, an anomaly drifting unnoticed in the Milky Way's shadow. But modern telescopes reveal the truth: this isn't just floating debris. It's a high-velocity relic from the cosmic dark ages, hurled across intergalactic space and now making its violent return. The numbers alone are staggering. Weighing in at 2 million solar masses, Smith's cloud will plow into the Milky Way's outer disk in roughly 30 million years, a blink in cosmic time. When it does, the collision will unfold like a slow-motion firestorm. The cloud's leading edge, already glowing with the heat of its own friction against interstellar gas, will compress further as it meets our galaxy's denser spiral arms. Shockwaves will ripple through the hydrogen sea, triggering cascades of star formation so intense they'll light up the galactic periphery like a string of fireworks. But these newborn stars won't just twinkle gently into existence. Many will be massive, volatile giants destined to explode as supernova within a few million years, peppering nearby space with lethal radiation. What makes this impending collision uniquely dangerous isn't the initial impact, but the aftermath. Studies using the Hubble Space Telescope reveal Smith's cloud is wrapped in a cocoon of dark matter, invisible gravitational scaffolding that will amplify its disruptive power. As this dark matter plows through the Milky Way's gas clouds, it won't just compress them. It will wrench their structure apart, distorting star-forming regions and potentially flinging existing stellar nurseries off course. The resulting turbulence could destabilize entire sectors of our galaxy's spiral arms, sending shockwaves that might ripple all the way to our solar neighborhood. Yet for all its destructive potential, Smith's cloud also carries the seeds of cosmic rebirth. The same violent compression that threatens existing systems will also forge new ones, enriching the galaxy with fresh generations of stars and planets. Some theories suggest our own Sun may have been born from similar intergalactic material billions of years ago, making this collision less an invasion and more like the Milky Way reclaiming long-lost building blocks. The cloud's trajectory, arcing back toward us from its mysterious ejection 2 billion years ago, hints at a vast cycle of matter exchange between galaxies, one where destruction and creation are inseparable partners in the cosmic dance. Astronomers now watch this approaching Leviathan with a mix of awe and apprehension. The Green Bank telescope's detailed maps show the cloud structure fragmenting as it nears, its outer layers already peeling away like cosmic streamers in the galactic wind. Current models predict our solar system will remain safely distant from the worst effects, but other stars might not be so lucky. For any hypothetical civilizations orbiting those suns, the coming millennia will bring escalating celestial fireworks, first a glow of ionized gas on the horizon, then bursts of new stars lighting up their skies, and finally, the searing flashes of supernova rewriting the chemistry of their worlds. Smith's cloud serves as a humbling reminder. The Milky Way isn't some isolated island universe, but an active participant in the intergalactic barter system. Matter flows between galaxies in great rivers we're only beginning to map, each exchange carrying the potential for both apocalypse and renaissance. As we track this primordial wanderer's final approach, we're glimpsing a process that has shaped galaxies since the dawn of time, where the universe's most dangerous objects aren't just destroyers, but the architects of tomorrow's cosmic landscapes. Hidden in the cosmic shadows since the dawn of time, primordial black holes are the universe's oldest predators, remnants of the Big Bang itself, where pockets of ultra-dense matter collapse directly into black holes without the death throes of a star. These ancient relics could be as small as a single atom, yet contain the mass of a mountain, their unimaginable density warping space into knots so tight not even light escapes. Unlike their stellar-born cousins, these dark stars, as some theorists call them, didn't form from collapsing suns. They're fossils from the universe's first chaotic moments, when quantum fluctuations in the newborn cosmos created microscopic regions of such extreme density that gravity simply won. Stephen Hawking theorized these black holes might not last forever. Through a bizarre quantum quirk near their event horizons, they emit faint radiation, now called Hawking radiation, slowly evaporating over eons. A pinhead-sized primordial black hole would shine with the heat of a nuclear reactor as it decays, its final moments culminating in a gamma-ray burst equivalent to millions of hydrogen bombs. But here's the terrifying catch: the smaller the black hole, the faster it evaporates. Most microscopic ones would have vanished by now. The survivors, those with masses greater than a small asteroid, would still be lurking, invisible and nearly undetectable except for the subtle ripples they leave in their wake. Now picture one of these ancient wanderers drifting into our solar system. Even a primordial black hole no larger than a grape but weighing as much as Earth would spell catastrophe. Passing through our planet, its gravity would create tidal forces so extreme they'd trigger earthquakes of unimaginable scale. As it traversed Earth's core, the black hole would compress and stretch the planet's mantle like putty, generating seismic waves that could rupture the crust globally. Cities would collapse into fissures, volcanoes would erupt in synchrony, and tsunamis would circle the globe, all from an object too small to see, the aftermath. A planet structurally gutted, its magnetic field disrupted, its atmosphere possibly stripped away by the gravitational disturbance. The real nightmare lies in their stealth. Without an accretion disk to glow, these black holes betray their presence only through gravitational lensing, bending the light of background stars, or the odd heat signature of Hawking radiation. Astronomers have searched for decades, using everything from gamma-ray telescopes to observations of ancient mineral deposits that might bear scars from close encounters. Some theories even suggest primordial black holes could account for part of the universe's missing dark matter, their collective gravity shaping galaxies while remaining utterly invisible. Yet for all their destructive potential, these cosmic ghosts might also hold keys to profound mysteries. Detecting one could reveal secrets about the Big Bang's conditions or prove Hawking radiation exists. Some physicists speculate advanced civilizations might even harness them as power sources or quantum computers. It's a staggering duality that the same objects capable of unraveling worlds might also illuminate the universe's deepest truth. So while we scan the darkness for these primordial killers, we're also searching for echoes from creation itself, carried in the gravity wells of the universe's first and most elusive shadows. Looming in the southern constellation Carina, Eta Carinae isn't just another star. It's a cosmic powder keg awaiting detonation. This hypergiant behemoth shines with 5 million times the luminosity of our Sun, yet its brilliance comes at a terrifying cost. Instability so profound it nearly tore itself apart during the 1840s in an event astronomers call the Great Eruption. Over just 20 years, Eta Carinae became the second brightest star in Earth's night sky, outshone only by Sirius despite being 7,500 light-years away. The energy released was equivalent to a supernova, yet somehow the star survived, ejecting enough material to form two solar systems and leaving behind the bizarre homunculus nebula. This hourglass-shaped cloud of gas and dust, expanding at speeds exceeding 2 million miles per hour, now cradles the star like the shrapnel of its own failed suicide attempt. But Eta Carinae's greatest spectacle and threat likely still lies ahead. Unlike regular supernova, this star's extreme mass and rapid rotation make it a prime candidate to explode as a hypernova, complete with deadly gamma-ray beams. Here's why that matters. If one of those beams points toward Earth during the explosion, the results would be catastrophic. Even from thousands of light years away, the radiation could strip our ozone layer within seconds, exposing all surface life to lethal ultraviolet bombardment. Marine ecosystems would collapse as phytoplankton, the foundation of oceanic food chains, perished en masse. Terrestrial plants would suffer radiation burns, triggering global crop failures. The resulting environmental devastation would make the asteroid that wiped out the dinosaurs look like a minor inconvenience by comparison. The star's bizarre behavior offers chilling clues about its unstable nature. Every 5.5 years, Eta Carinae's brightness fluctuates wildly as its smaller companion star swings close in a deadly orbital dance. During these encounters, the star's powerful stellar winds collide with enough force to generate X-ray flares detectable across the galaxy. Observations from NASA Chandra X-ray Observatory reveal shockwaves rippling through the surrounding nebula like echoes of a coming apocalypse. Even more ominous is the star's erratic mass loss, currently shedding material equivalent to 100 Earth masses every year. This rapid disintegration means Eta Carinae has likely already crossed the theoretical stability limit where stars can no longer sustain themselves against their own radiation pressure. What makes this stellar monster especially frightening is its alignment relative to Earth. The homunculus nebula's axis, formed during the Great Eruption, points toward us at roughly 45 degrees, meaning when the hypergiant finally explodes, there's a significant chance one of its gamma-ray jets could intersect our solar system. Astronomers calculate we might receive as much as 100,000 times the lethal radiation dose for humans during such an event. The gamma rays themselves would last mere seconds, but their atmospheric effects would persist for years, potentially triggering an ice age through nitric oxide-induced global cooling. Yet Eta Carinae isn't just a destroyer. The same violent processes that make it dangerous have also seeded its surroundings with heavy elements crucial for life. The homunculus nebula shines with the spectral fingerprints of lithium, calcium, and titanium elements forged in the star's turbulent heart and now cycling back into the interstellar medium. In a poetic twist, the same explosion that could devastate distant planets might eventually fertilize new ones with the building blocks of future civilizations. As we monitor this ticking time bomb through space telescopes, we're witnessing stellar evolution at its most extreme, a laboratory for physics that can't be replicated anywhere else in the universe. Every flicker and flare from Eta Carinae carries coded messages about the final days of massive stars, offering glimpses of processes that shaped the early cosmos. For now, the hypergiant continues its slow-motion self-destruction, reminding us that the universe creates its most spectacular wonders hand in hand with its deadliest threats, and that sometimes the difference between the two is simply a matter of perspective and distance. In the subatomic realm, where quarks dance in protons and neutrons, there exists a theoretical nightmare, strangelets. These are specks of exotic matter composed not of ordinary up and down quarks, but of strange quarks, a heavier and far more unstable variety. Under extreme pressures like those inside neutron stars, some theories suggest these strange quarks could form stable configurations, creating strange matter that behaves unlike anything in our everyday experience. The frightening twist: if stable, this matter might have a horrifying property. the ability to convert normal matter it touches into more strange matter, like a nuclear chain reaction at the quark level. This isn't just wild speculation. Scientists at Brookhaven National Laboratory's relativistic heavy ion collider, RHIC, have actively searched for strangelets during high-energy particle collisions. Their experiments slam gold ions together at nearly light speed, briefly recreating conditions similar to the early universe or neutron star interiors, environments where strangelets might theoretically form. So far, no confirmed detections exist, but the search continues because the implications of their existence are staggering. Now imagine a doomsday scenario, a strangelet drifting through space, perhaps ejected from a neutron star collision, eventually making contact with Earth. Upon arrival, it begins converting atoms at the point of impact, transforming their quarks into strange quarks. The converted matter releases energy, fueling further conversions. The process spreads exponentially. First, a grain of sand's worth of material becomes strange matter, then a pebble, then a boulder. Within hours, the entire planet could be transmuted into a hot, dense sphere of strange matter, its original structure erased at the most fundamental level. The conversion wouldn't stop at Earth. It could leap to the Moon, nearby planets, even the Sun, rewriting the solar system into an unrecognizable state. The terrifying elegance of this scenario lies in its physics. Strange matter, if stable, would be more energetically favorable than normal matter, meaning the universe itself might prefer it. Some theories even propose that certain neutron stars could actually be strange stars, their cores entirely composed of this exotic substance. If so, collisions between these objects could spray strangelets across the galaxy like cosmic shrapnel, each fragment carrying the potential to trigger a chain reaction in any ordinary matter it encounters. Yet there's hope in the numbers. Statistical models suggest strangelets, if they exist at all, are likely rare or unstable enough that Earth has survived billions of years without encountering one. Cosmic ray observations haven't detected the telltale signatures of strange matter, and experiments continue to place tighter limits on their possible creation. But the fact that we've seriously considered the risk, even adjusting collider experiments to minimize theoretical dangers, shows just how seriously science takes the potential existence of these ultra-dense, world-ending specks. In the end, strangelets represent one of the most unsettling possibilities in physics, that the building blocks of reality itself might have a more stable, more lethal configuration waiting to be triggered. They remind us that the universe's deadliest threats aren't always the colossal explosions or gravitational monsters. Sometimes, they're the smallest, most elusive fragments, carrying the power to redefine existence itself. Stretching across the cosmos like invisible scars from the birth of the universe, cosmic strings are hypothetical defects in spacetime so dense they warp reality itself. Picture the fabric of the universe as a sheet of ice freezing over. When water crystallizes, cracks sometimes form between regions that cooled at different rates. In those first chaotic moments after the Big Bang, physicists believe spacetime may have undergone a similar phase transition, leaving behind one-dimensional cracks of pure energy thinner than a proton, but with the mass of entire galaxies packed into every mile. These aren't just theoretical oddities. If they exist, their gravitational footprints could rewrite our understanding of physics. A cosmic string's true terror lies in its incomprehensible density. While black holes cram matter into finite points, strings are thought to possess infinite density along their length, a thread of pure spacetime curvature with no thickness whatsoever. Their gravitational influence would be so extreme that a string just a kilometer long could outweigh Earth. Moving near one at relativistic speeds would warp time itself. Astronauts circumnavigating a string might return to find centuries had passed on Earth. But the most startling effect would be gravitational lensing on a scale dwarfing anything black holes produce. Hubble Space Telescope observations have catalogued bizarre, duplicate images of distant galaxies that can't be explained by conventional lensing. Some astronomers speculate these could be light bent around cosmic strings like headlights twisting through a funhouse mirror. The hypothetical danger comes from their motion. As these relic defects vibrate at near light speeds, they might occasionally intersect, forming closed loops that collapse in bursts of gravitational waves. Advanced detectors like LIGO have picked up mysterious wave patterns that don't match known black hole or neutron star mergers. Some theorists whisper these could be the death throes of ancient cosmic strings. A close encounter with such an event would be apocalyptic. The gravitational shockwaves could rip planets from their orbits or strip atmospheres like leaves in a hurricane. Even more unsettling is the possibility that string loops might decay into high-energy particle cascades, bathing nearby space in lethal radiation without warning. Yet cosmic strings also represent a tantalizing opportunity. Their unique properties could explain some of cosmology's greatest mysteries, from the universe's large-scale structure to anomalies in the cosmic microwave background. Some models even suggest they might serve as natural time machines, their extreme space-time curvature potentially creating closed time-like curves where cause and effect break down. Whether as destroyers or cosmic tools, these space-time defects remind us that the universe's earliest moments may have left behind more than just fading radiation. They may have woven traps into the very fabric of reality, waiting to be discovered, or to ensnare the unwary. Silent and relentless, HOP 85605 barrels toward us at nearly 30 kilometers per second, a runaway star ejected from its birthplace by gravitational chaos. Currently 14 light-years away in the constellation Hercules, this orange dwarf might seem harmless compared to cosmic titans like black holes or quasars. But its true threat lies not in its brilliance or size, but in its trajectory. Astronomical projections suggest it will make its closest approach to our solar system in about 240,000 years, slicing through the outer Oort cloud at a mere 0.13 light-years away, 3 times closer than our current nearest stellar neighbor, Proxima Centauri. The consequences of this stellar flyby read like a slow-motion apocalypse. The Oort cloud, that vast shell of icy planetesimals surrounding our solar system, extends nearly a light-year into space, a gravitational minefield where trillions of frozen remnants from the solar system's formation lie dormant. Normally, these objects remain in stable orbits, but HOP 85605's gravity could act like a celestial cue ball, scattering comets inward in a deadly game of cosmic billiards. Simulations show even subtle gravitational nudges could destabilize millions of these icy bodies, sending some careening toward the inner solar system over thousands of years. What makes this scenario uniquely terrifying is its inevitability. Unlike rogue black holes or gamma-ray bursts, we've already mapped HOP 85605's path with remarkable precision, and there's nothing we can do to alter it. The star's mass, roughly half that of our Sun, ensures its gravitational influence will ripple through the Oort cloud's delicate balance. Some models predict a 300% increase in the number of long-period comets entering the inner solar system for millennia after its closest approach. Historical records hint we may have survived similar encounters before. The late heavy bombardment 4 billion years ago and certain spikes in Earth's cratering record could trace back to previous stellar intruders. Yet the danger isn't uniform. Much depends on the angle of HOP 85605's passage and the density of Oort cloud debris it disrupts. A direct gravitational resonance could funnel comets into a concentrated storm, while a glancing blow might only slightly elevate impact risks. Even so, astronomers calculate a non-trivial chance of at least 1 kilometer-sized impactor being redirected toward Earth within 500,000 years of the flyby, a rock large enough to trigger global climate disruption comparable to the asteroid that wiped out the dinosaurs. There's an eerie irony here. The same process that might one day rain destruction on our planet also plays a crucial role in galactic ecology. Runaway stars like HOP 85605 redistribute heavy elements across the Milky Way, and their gravitational kicks can trigger star formation in interstellar clouds. Some theories even suggest life's building blocks might hitchhike on comets dislodged by such stellar encounters, meaning this potential harbinger of doom could also be an unwitting agent of cosmic fertilization. As we track HOP 85605's inexorable approach, we're witnessing a phenomenon that has shaped solar systems since the dawn of the galaxy. Its passage will test Earth's resilience against forces beyond our control, reminding us that the universe doesn't just threaten us with sudden cataclysms. Sometimes danger approaches patiently over epochs, written in the slow dance of stars we're only beginning to understand. While quasars dominate the centers of distant galaxies, their smaller but equally lethal cousins lurk closer to home microquasars. At the top of this terrifying class stands SS433, a binary system located 18,000 light-years away in the constellation Aquila. This cosmic powerhouse consists of a black hole or neutron star locked in a deadly dance with a massive companion star, siphoning off its outer layers into a superheated accretion disk. But what truly sets SS433 apart are its twin jets beam like outflows of plasma screaming into space at 80% the speed of light, twisting through the cosmos like a pair of interstellar fire hoses with minds of their own. These aren't static beams. Every 162 days, the jets complete a full precession cycle, wobbling in a conical pattern that traces circles on the sky. This bizarre motion stems from the accretion disk's tilt relative to the system's orbital plane, creating a gyroscopic effect that sweeps the jets across space like the beam of a cosmic lighthouse. The result, a spiral of death stretching light years into interstellar space, where particles accelerated to relativistic energies collide with ambient gas, generating X-rays visible across the galaxy. The raw power packed into these jets defies comprehension. Chandra X-ray observatory measurements reveal temperatures exceeding 50 million degrees Celsius within the outflow, hot enough to vaporize any known material instantly. Worse still, the jets carry heavy atomic nuclei like iron, accelerated to energies that make Earth's most powerful particle accelerators seem like toys. If a planet found itself in the path of these beams, the consequences would unfold in three nightmarish phases. First, the initial X-ray flash would ionize the upper atmosphere, stripping away ozone and exposing the surface to lethal ultraviolet radiation. Next, the relativistic particles would arrive, bombarding the planet with continuous radiation comparable to standing inside a nuclear reactor core. Finally, the jet's kinetic energy would blast away portions of the atmosphere entirely, leaving behind a desiccated husk where oceans once existed. SS433's true danger lies in its unpredictability. Unlike the steady jets of larger quasars, microquasar outflows flicker and flare as their accretion rates vary. In 2010, astronomers observed a sudden hundredfold increase in its X-ray emissions, a tantrum that, had it occurred closer, could have sterilized an entire sector of space. The system's precession adds another layer of horror. Planets orbiting at what might seem a safe distance could suddenly find themselves in the crosshairs as the jets swing their way. Even more unsettling is the possibility that SS433 isn't unique. The Milky Way likely contains hundreds of similar microquasars, many still undetected behind veils of interstellar dust. Yet for all their destructive potential, microquasars like SS433 serve as crucial natural laboratories. Their smaller size and faster changes allow astronomers to study jet formation processes that would take millennia to observe in full-blown quasars. The precessing jets in particular offer insights into how spinning black holes interact with their accretion disks, a phenomenon that might explain similar behaviors in supermassive cousins across the universe. There's poetic symmetry here. The same mechanisms that could annihilate worlds also help us unravel the universe's deepest mysteries. So while we respect these miniature monsters from a safe distance, we also recognize their role as cosmic teachers, demonstrating fundamental physics with a violence no laboratory could ever replicate. Hidden beneath the smooth expansion of our universe lies a terrifying possibility. Dark energy isn't uniformly distributed. Imagine pockets of space where this mysterious force, already accelerating cosmic expansion, grows unnaturally strong. These dark energy overdensity regions could become cosmic time bombs, stretching the fabric of reality beyond recognition. In their most extreme form, they might trigger a premature Big Rip, a scenario where expansion accelerates so violently it doesn't just push galaxies apart but tears apart stars, planets, and eventually even atoms themselves in a final apocalyptic instant. Most cosmologists assume dark energy operates evenly across the cosmos, its repulsive force acting as a gentle but relentless pressure on spacetime. Yet if fluctuations exist, dense knots where dark energy's strength spikes, the consequences would rewrite the universe's fate. Picture a bubble of runaway expansion forming in deep intergalactic space. Within this zone, the repulsive force grows exponentially, pushing neighboring galaxies away faster than light can bridge the gap. Isolated and alone, these galaxies would vanish from each other's skies as space between them stretches faster than photons can travel. But the real horror begins if such a region expands outward, consuming everything in its path like a cosmic wildfire. The Big Rip scenario typically belongs to the far future, trillions of years from now, but a dark energy overdensity could fast-track this doom. As the overdensity grows, its expansion force would overwhelm gravity's grip first on galaxy clusters, then individual galaxies. Milky Way's spiral arms would unravel as stars are flung into the void. Next, solar systems would disintegrate, planets torn from their suns as the space between them inflates faster than orbital speeds can compensate. Finally, in the last milliseconds, atomic bonds themselves would fail, nuclei ripped apart as the fundamental forces that hold matter together are overcome by the universe's violent stretching. Evidence for such overdensities remains speculative, but tantalizing clues exist. Astronomers mapping the universe's large-scale structure have noted strange supervoids, regions hundreds of millions of light-years wide where galaxies are suspiciously sparse. Some theories suggest these voids might be areas where dark energy's influence is stronger, pushing matter away more aggressively. Others point to anomalies in the cosmic microwave background, subtle temperature fluctuations that could hint at uneven dark energy distribution dating back to the Big Bang. Even the controversial Hubble tension, discrepancies in measurements of the universe's expansion rate, might find an explanation in dark energy's patchwork nature. The most unsettling aspect, if such an overdensity began expanding toward us, we'd have no warning until it was too late. The boundary would advance silently, crossing our cosmic horizon without any signal preceding it. One day, astronomers might notice distant galaxies disappearing faster than expected, the first hint of the approaching cascade. By the time closer structures began accelerating unnaturally, the overdensity's grip would already be unstoppable. Unlike asteroid impacts or supernova, this threat offers no possibility of deflection or shelter. The universe itself would become the enemy, its fundamental laws turned against existence. Yet in this potential apocalypse lies profound insight. Studying dark energy's possible irregularities forces us to confront the limits of our cosmic models. If overdensities exist, they could explain why some regions of the universe appear older than they should be, or why certain galaxy motions defy gravitational expectations. Some theorists even propose that dark energy's strength might evolve over time, or space, meaning our universe's fate could vary dramatically by location. One corner of reality might face the Big Rip while another continues on placidly for eons. This duality captures the essence of cosmology's grandest mysteries. The same force that accelerates galaxies apart might also hold the seeds of their dissolution. Whether uniform or patchy, dark energy remains the ultimate arbiter of the universe's destiny, a reminder that existence balances on a knife's edge between endurance and annihilation. And as we peer into the void, searching for clues in the light of distant supernova or the whispers of ancient radiation, we're not just mapping the cosmos. We're reading our own expiration date, written in the invisible hand of the universe's most enigmatic force. Glistening in the constellation Draco like a cosmic jewel, the Cat's Eye Nebula might appear serene through a telescope, but this stellar graveyard hides a violence that defies its delicate name. Hubble's razor-sharp images reveal an intricate onion skin structure, layers of gas expanding outward at 1,000 kilometers per second, fast enough to cross the United States in under 4 seconds. These aren't gentle wisps of cosmic recycling. They're shockwaves from a dying star's final tantrum, blasting space with enough ultraviolet radiation to sterilize entire planetary systems. At the nebula's heart lies a white dwarf so hot its surface burns at 80,000 degrees Celsius, a searing remnant of the star that once was. As it pulses with unstable energy, ultraviolet flares erupt outward, ionizing the surrounding gas into a lethal glow. The colors we admire, vibrant blues and haunting greens, are actually warning signs, emissions from oxygen and hydrogen atoms being ruthlessly torn apart by radiation. The same process that paints these ethereal hues would, at close range, shred DNA and boil away atmospheres. The cat's eye's concentric shells tell an even darker story. Each ring represents a previous eruption, evidence of the dying star violently shedding its outer layers every 1,500 years. The outermost halo, stretching over 3 light years, carries the scars of the earliest explosions, a timeline of stellar agony frozen in gas. When Hubble's spectrographs analyzed these layers, they detected atoms of neon, argon, and even iron being catapulted into space, elements forged in the star's core now weaponized as high-velocity shrapnel. Most chilling of all is the nebula's central jet, a narrow beam of material screaming outward at nearly half the speed of light. This cosmic blowtorch, aligned perpendicular to the expanding shells, suggests the dying star isn't just expelling material, it's firing bullets. Astronomers believe intense magnetic fields channel these jets, focusing the star's death throws into beams that could punch through interstellar clouds like a particle accelerator from hell. Any planet caught in their path would endure a bombardment of high-energy protons, a relentless assault that could last for centuries. Yet amid this destruction lies an eerie beauty. The cat's eye symmetry, sculpted by complex interactions between stellar winds and magnetic fields, offers a glimpse into processes that will one day shape our own sun's demise. The heavy elements it scatters, carbon, nitrogen, oxygen, will eventually seed new stars and planets. This duality defines so many of the universe's deadliest phenomena. The same forces that erase worlds also build the ingredients for new ones. So while we marvel at Hubble's portraits of this cosmic masterpiece, we're also staring at a future that awaits every star, ours included. A reminder that in space, even death can wear a dazzling mask. Burning with the fury of a cosmic blowtorch, Zeta Ophiuchi isn't just another star. It's an ultraviolet death machine hurtling through space at 30 kilometers per second. This blue O-type giant radiates with 80,000 times the luminosity of our sun, its surface churning at 50,000 degrees Celsius. But raw power isn't what makes Zeta Oph truly terrifying. It's the apocalyptic hurricane of charged particles screaming from its surface at 9 million kilometers per hour. These aren't gentle solar breezes, they're supersonic plasma tsunamis capable of stripping away planetary atmospheres light years away. NASA's Spitzer Space Telescope captured the star's violence in crisp infrared detail, a vast bow shock stretching 16 light-years across, sculpted from interstellar dust like a cosmic wake. This glowing arc marks where Zeta Off's relentless stellar wind slams into surrounding gas, creating a shock front so powerful it heats material to thousands of degrees. The force behind this bow shock would be like standing in front of a sandblaster firing at 100 times the speed of sound. Any hypothetical planet orbiting this star would be scoured down to bare rock within millennia, its oceans boiled into space and its crust melted by relentless X-ray bombardment. What makes O-type stars like Zeta Ophiuchi especially deadly is their short, violent lifespans. While our sun will burn steadily for 10 billion years, these blue giants live fast and die young, exploding as supernova after just a few million years. In stellar terms, that's barely a cosmic eye blink. When Zeta Off finally detonates, the explosion will outshine entire galaxies for weeks, flooding nearby space with enough gamma radiation to sterilize any emerging planetary systems within 100 light-years. Its core will likely collapse into a neutron star or black hole, leaving behind a remnant as lethal as the star itself once was. The real nightmare begins when we consider Zeta Off's trajectory. Currently 460 light-years away, this runaway star was likely ejected from its birthplace by gravitational interactions in a dense star cluster. Now it barrels through the galactic plane like a rogue bullet, its path potentially crossing through molecular clouds where new stars and planets form. Where it passes, it sows chaos, compressing gas to trigger star formation in some regions while shredding protoplanetary disks in others. It's the ultimate cosmic double-edged sword, a destroyer of worlds that simultaneously catalyzes the birth of new ones. Astronomers have identified similar O-type fugitives throughout the Milky Way, each with its own apocalyptic bow shock. Some, like A Aurigui, blaze through space even faster, their ultraviolet fury creating glowing nebulae that serve as both warning beacons and tombstones for any planetary systems in their path. What these stellar outlaws teach us is that the universe doesn't just threaten us with distant cataclysms. Danger can come barreling through our neighborhood at any moment, rewriting the fate of solar systems with nothing more than the silent, unstoppable momentum of a star that lost its way. Yet within their violence lies creation. The heavy elements forged in their cores and scattered by their explosions will one day become part of new stars, new planets, perhaps even new life. The same forces that erase worlds also make new ones possible, a paradox as beautiful as it is terrifying. From gamma-ray bursts that could strip our ozone layer in seconds to magnetars capable of frying planets with their magnetic fury, the universe isn't just vast, it's armed with celestial doomsday devices. Let's revisit the 5 most immediate cosmic threats lurking in our galactic backyard. First, gamma-ray bursts, those hyper-focused beams of annihilation from collapsing stars or neutron star mergers, capable of triggering mass extinctions from thousands of light-years away. Second, magnetars spinning neutron stars with magnetic fields so intense they induce starquakes, releasing years' worth of solar energy in milliseconds. Third, rogue black holes like Gaia BH1, invisible nomads wandering unchecked, their gravity capable of hurling entire solar systems into chaos. Fourth, hypernovae, stellar explosions orders of magnitude more powerful than supernova, their lingering radiation able to cook planetary surfaces for decades. And fifth, dark matter anomalies, hypothetical but terrifying clumps that might decay into lethal radiation without warning. Yet these apocalyptic forces aren't just agents of destruction, they're the universe's architects. GRBs seed space with heavy elements, magnetars may forge the building blocks of life, and even rogue black holes play a role in shaping galactic evolution. This grand paradox defines our cosmos. The same violence that sterilizes worlds also makes new ones possible. In the end, we're left with a humbling perspective. We exist not despite these dangers, but because of them. The universe doesn't guarantee safety, but it does offer spectacle on a scale we're only beginning to understand. So which of these cosmic monsters unsettled you the most? The silent hunger of black holes or the electric fury of magnetars? Drop your thoughts below, and if staring into the abyss left you craving more cosmic mysteries, hit subscribe. Because in the grand theater of the universe, every discovery reveals new wonders and new ways the cosmos keeps us deliciously terrified.